This is the second video in Unit 5 in the gases series, and in this video we are going to cover the kinetic molecular theory. The kinetic molecular theory is really a pretty simple model, and it's the theory behind the thermodynamic behavior of matter. Specifically, though, we are going to look at how it applies to gases. KMT attempts to explain the properties of an ideal gas, a gas that is behaving the way that we expect it to. This model is based on observed behavior of particles and a bit of speculation. The first assumption of KMT is that the particles are so small compared with the distances between them that the volume of the individual particles can be assumed to be negligible. In other words, for a gas to be ideal, the particles must have plenty of room to move around, and they must not be so close together that the gas molecules themselves have relative volume. The second assumption, the particles are in constant motion. The collisions of the particles with the walls of the container are the cause of the pressure exerted by the gas. As we stated earlier in class, the collisions of the gas particles with the side of the container cause measurable pressure on the container walls. In order for this to be true, gas particles must always be in motion, and in this case, random motion. Assumption number 3. The particles are assumed to exert no forces on each other. They are assumed neither to attract nor repel each other. So in other words, if the gas particles are moving fast enough and or far enough apart, they cannot exert dipole forces or any other attractive forces for that matter on each other. And number 4, and this is a new one for us. The average kinetic energy of a collection of gas particles is assumed to be directly proportional to the Kelvin temperature of the gas. As you probably already know, though, kinetic energy increases with temperature. The higher the temperature, the more the gas particles are moving. So if we look at the assumptions of KMT, we can see how KMT explains the individual gas laws. Boyle's law addresses the relationship between volume and pressure. As the volume decreases, the gas particles will hit the walls more often, thus increasing the pressure. Charles' law isolates the relationship between temperature and volume. When the gas is heated to a higher temperature, the speeds of its molecules increase and thus hit the walls more often and with more force. Volume and/or pressure will increase. Avogadro's law, an increase in number of gas particles at the same temperature increases the number of collisions and would cause the pressure to increase if the volume were constant. And finally, Dalton's law. All gas particles are independent of each other, and that the volumes of the individual particles are really unimportant. Identities of these gas particles do not matter. You can combine several gases into one container and get the same observations if you have the same amount of just one gas. There is just one more thing that I want to discuss in this video. I want to be a little more specific with the fourth assumption of KMT. Kelvin temperature directly indicates the average kinetic energy of the gas particles. The exact relationship between temperature and average kinetic energy can be expressed in a formula. Kinetic energy is 3/2 RT. R is the constant, 8.3145 joules per Kelvin mole. This is the exact same R as the gas laws are, except the units are different, and T is in Kelvin. Please note in the equation that only temperature in Kelvin is a variable when solving for kinetic energy. The rest of them are just constants. You should probably write this equation down or at least become familiar with it so that we can solve problems with it. And this concludes our second video.